RTX 4080 unlaunch. The RTX 4080 12GB version holds the rare honor of being a product that existed, then unexisted. NVIDIA announced it in 2022 alongside the real RTX 4080, and on paper, it looked like a slightly smaller sibling. In reality, it was a completely different graphics processor pretending to be family. The 12GB model used a smaller chip with far fewer cores and a narrower memory bus. Performance was closer to a 4070 tier card, but the price was $899. That's just $200 less than the genuine 4080, which is the hardware equivalent of selling a bicycle for the price of a motorcycle because they both have wheels. Reviewers instantly called it out. Even NVIDIA's most loyal fans couldn't defend it. The naming was misleading, the pricing insulting, and the whole launch felt like a bad April Fool's joke that wouldn't end. The backlash got so bad that NVIDIA did something no one expected. They unlaunched it. Yes, that's a real word now. They literally canceled a product after announcing it. Officially, NVIDIA said it was not named right. Unofficially, it was a marketing disaster so loud that pretending it never happened seemed like the best option. A few months later, the exact same GPU reappeared, now called the RTX 4070 Ti, with a slightly more honest label and the same silicon. The unlaunch taught an important lesson. You can't fix bad branding with a driver update. Sometimes, the only patch available is pretending the product never existed. NVIDIA GTX 970 VRAM. The GTX 970 launched in 2014. At first, looked like one of the best deals in GPU history. High-end performance for a mid-range price. What could possibly go wrong? Everything, apparently. NVIDIA advertised the card with 4GB of VRAM. That's what everyone expected. That's what everyone paid for. And that's what NVIDIA printed on the box. What they didn't print was the fine detail. The memory wasn't evenly accessible. 3.5GB ran at full speed, and the remaining ½ GB was so slow it might as well have been an emotional support buffer. This split memory design meant that once a game used more than 3.5GB of VRAM, performance suddenly tanked. Frame rates dropped, stuttering began, and users realized their 4GB card was more of a 3.5GB plus a SAT appendage. The internet noticed. Hard. Benchmarks exposed the flaw. Tech forums exploded, and 3.5GB became a meme overnight. NVIDIA's explanation didn't help. Apparently, it was by design. So was the outrage. Class action lawsuits followed, and while NVIDIA settled, the PR damage was permanent. To be fair, the GTX 970 still performed well for most games of its era, as long as you didn't cross the forbidden 3.5GB line. But once you did, the experience turned into a PowerPoint presentation. It remains a reminder that clever engineering is great, but clever marketing will always get caught eventually. Intel NetBurst, Pentium 4. The early 2000s were a magical time, when Intel decided that more megahertz automatically meant more performance. The result was NetBurst, the architecture behind the Pentium 4. It was built on one brilliant principle. If you can't make your CPU smarter, just make it louder. NetBurst's secret sauce was an extremely long instruction pipeline, up to 31 stages on some versions. Longer pipelines meant higher clock speeds, at least in theory. In practice, every time the CPU guessed a branch wrong, it had to dump all that work and start again. That's like sprinting up a staircase, realizing you're in the wrong building, and starting over repeatedly at 3 billion times per second. Intel bragged about the Pentium 4's gigahertz leadership, and they got it. The chip screamed along at 3.8 GHz while losing to AMD's slower Athlon 64. It turns out raw speed doesn't matter much when half your effort goes into cleaning up your own mistakes. Then there was the heat. Prescott-based Pentium 4s routinely hit over 100 watts of TDP, which made them great space heaters and terrible processors. Users joked that their PCs could double as portable ovens, and they weren't far off. Some laptops using Pentium 4 chips were known to cook legs and batteries with equal enthusiasm. Intel eventually gave up and replaced NetBurst with the core architecture, effectively admitting that chasing clock speed for its own sake was like trying to win a marathon by setting yourself on fire. AMD Bulldozer. If Intel's NetBurst was a bonfire of wasted watts, AMD's Bulldozer was an over-engineered science project that forgot it needed to be good at, well, computing. Released in 2011, Bulldozer was supposed to put AMD back on top with an all-new module design. Each module contained 2 integer cores sharing one floating point unit. AMD proudly called this an 8-core CPU. Everyone else quickly discovered it behaved more like 4 cores that couldn't stop arguing over who gets to do the math. math. The theory was that shared resources would make the chip efficient. The reality was that every time both threads wanted to do floating point work, performance fell flat on its face. Games, single-threaded software, even some multitasking, all ran slower than on the previous Phenom 2 chips. It was like upgrading your car only to find out the new one can't go uphill. Then came the heat. The FX9590 drew up to 220 watts, roughly the output of a small space heater, just to stay barely competitive with Intel's mid-range i5. AMD's marketing showed proud 5 GHz numbers, conveniently skipping the part where those numbers came with a jet engine cooler attached. Developers weren't amused either. Programs expecting 8 true cores ran inconsistently, and optimization was a nightmare. Reviews were brutal, calling Bulldozer one of the most disappointing CPUs in modern history, and not without reason. Still, credit where it's due. Bulldozer's failure forced AMD to hit the reset button and rethink everything. That rethink became Ryzen. So yes, Bulldozer was a disaster, but at least it was the kind of disaster that teaches you to never build the same disaster twice. Intel Itanium. Imagine designing a CPU so advanced that no one on Earth could actually use it. That was Intel's Itanium, a processor line so ambitious, it accidentally invented the concept of obsolescence at launch. Itanium was supposed to replace x86 entirely. Intel called it IA64, a brand new 64-bit architecture built for the glorious future of computing. The only problem was the rest of the world wasn't invited. It used a system called Explicitly Parallel Instruction Computing, or EPIC, which basically meant the compiler had to do all the hard work of figuring out which instructions could run in parallel. Compilers, being the sensible kind, decided they wanted no part of this. Software developers hated it. Writing or porting code for Itanium was like translating Shakespeare into Klingon. Theoretically possible, but nobody wanted to do it. Running x86 applications required emulation, which was both slow and painful. In benchmarks, the supposedly futuristic Itanium often lost to cheaper Pentium chips that didn't require a PhD and regret to use. And let's talk price. Itanium systems cost thousands, sometimes tens of thousands of dollars. Intel marketed it as an enterprise powerhouse, but the only people who ever bought it were data centers running HPUX, or very confused IT departments. Everyone else just quietly ignored it. Intel kept the project alive for almost 2 decades, mostly out of stubbornness, before finally killing it in 2021. In the end, Itanium's biggest achievement was proving that even a trillion-dollar company can't force the world to adopt something no one asked for. Rambus RDRAM. At the turn of the millennium, Intel and Rambus decided they'd reinvent computer memory. The result was RDRAM, an ultra-expensive, over-engineered memory technology that promised incredible speed and delivered incredible inconvenience. On paper, RDRAM had high bandwidth. In practice, its latency was awful. The memory bus ran in series, meaning every module depended on the next one in line, like Christmas lights that stop working when one bulb dies. You couldn't leave a slot empty either. If you didn't install a full set of sticks, you had to use continuity modules, dummy sticks of fake RAM whose only purpose was to let the system boot. Yes, a product that required pretend RAM to function. Truly revolutionary. Then came the price. RDRAM was several times more expensive than DDR-SDRAM, which performed almost as well in real workloads and didn't require a PhD in motherboard voodoo. Intel forced early Pentium 4 boards to use it anyway, presumably out of contractual optimism. Consumers responded by not buying those motherboards. And the heat. RDRAM modules shipped with metal heat spreaders because the chips ran hot enough to need armor plating. Meanwhile, DDR quietly improved generation after generation until RDRAM was both slower and more expensive. A truly impressive combination. By 2003, DDR had completely taken over. Rambus tried to save face by suing other companies over patents, which is usually the corporate version of rage quitting. The whole experiment became a museum exhibit in how next generation can age faster than milk. FireWire. FireWire was Apple's early attempt to give the world a smarter, faster alternative to USB. And to be fair, it worked, as long as you were willing to pay for the privilege. Introduced in the late 1990s, FireWire offered faster speeds, daisy chain support, and the ability to power devices directly. It was technically superior to USB 1.1 and even early USB 2.0, but as history shows, technically superior and financially doomed often go hand in hand. Apple charged licensing fees for every FireWire port port, chip, and cable. A bold move in an era when USB was free and backed by Intel, Microsoft, and literally every PC manufacturer on the planet. So, while FireWire was showing off its high-speed transfers, USB quietly took over the world by being cheap and everywhere. For a while, FireWire found a niche in video editing. Mini DV cameras loved it, but outside of that bubble, almost no one cared. It was faster, sure, but not that much faster, especially once USB 2.0 caught up. Consumers voted with their wallets, and FireWire was left holding an expensive plug nobody wanted to use. And then there was the name. FireWire sounded exciting, maybe too exciting. It occasionally lived up to its name by frying ports if you hot-plugged certain devices. Apple eventually dropped it in favor of Thunderbolt, which offered the same idea, but without the spontaneous combustion feature. In the end, FireWire proved that good engineering can't overcome bad business decisions, especially when you try to charge people for using a cable. Samsung 840 EVO SSD. The Samsung 840 EVO was a hero at launch, a fast, affordable SSD that brought solid-state storage to the masses. Then, slowly but surely, it turned into the digital equivalent of a midlife crisis. At first, everything was perfect. The drive flew through benchmarks and made hard drives look prehistoric. Then users noticed something weird. Older files, the ones you hadn't touched for months, started taking ages to read, not a bit slower. We're talking seconds instead of milliseconds. On an SSD, that's like watching a sports car stall at a green light. The culprit was the TLC NAND flash inside. It stored 3 bits per cell, which made it cheap and dense, and unfortunately, unstable over time. As data sat untouched, the tiny electrical charges representing those bits faded. When the controller tried to read them back, it hesitated, guessed, and sometimes got it wrong, causing massive slowdowns. Samsung first denied the issue, then rolled out a firmware fix that periodically refreshed old data. It worked, briefly. A few months later, the slowdown returned. Another patch came, then another. By the third fix, it felt less like an update and more like a regular oil change. Eventually, Samsung moved on to newer models with better NAND and controllers, leaving the 840 EVO's reputation somewhere between legendary and cautionary tale. It still works today, if you're patient. A perfect example of how even the best tech company can be humbled by the laws of physics and a little bit of overconfidence. And when hardware doesn't fail, software still can. The biggest operating system disasters are on screen right now.